All right. Good morning. Good afternoon. Good evening. Hi, everybody. Say hi in the chat. Say your name and where are you dialing from? Right. Good to have you. Come on. Hi, Joe, Kalim, Akash, Benson, Kalim, Nadia. Hi, Javer. Right. Rashid, Lalit. Wow. That's a lot. Wow. Saudi Arabia. Wow. Malaysia, next door. Yeah. Algeria. Hi, Lee Yun Long. Singapore. Wow. Really, neighbor. I'm from Singapore. Dialing from Singapore. India. All right. All right. Let's get started. Thank you all for joining. Excited to be here. This is a session which I also looking forward. I've not I've not I don't have experience in APC. This is something which is I'm also curious, right? I want to know more, and we have a great expert, Doug here, right? So let's get started. Right. So the title is "Get the Most from Your Plan with APC." Right. Right. A quick introductions. Uh, this is myself, Fauzi, right? So I study chemical engineering from Indonesia in Bandung, graduated 2002, right? Then I start working with an EPC company, an upstream EPC company called McDermott, right? I moved to Singapore around 2006, then continue working with McDermott. Then I joined Wally, right? While joining Wally, I also did my MBA part time with National University of Singapore, right? In Wally, I've done a few different types of project, mainly around feed of LNG regasification, some refinery and chemicals, right? And later parts of my years in Wally, I do more of feasibility study, due diligence, financial modeling, right, for LNG terminals, right? Then I joined for a short while with Vopak. It's a terminal operator, so they operate 5 terminals here in Singapore, right? I was working on a project trying to build LNG terminal, a second LNG terminal in Singapore, right? Then I joined Aspen 2019 as a solution consultant. I focus on engineering solutions of Aspen, which is process simulations and a few other tools, right, like cost estimations, right? So I work across Southeast Asia, right? So that's myself, right? So let's introduce the expert today. So we are honored to have Mr. Douglas McCallum, right, the principals and founders of McCallum's Value Partners, which focus on improving industries through adopting APC. Previously, he was the global practice director at Aspen. As a seasoned chemical engineering and business strategist, Mr. McCallum led the best practices for Aspen APC business in this capacity. Before this role, Mr. McCallum was the global advisor for APC. Additionally, Mr. McCallum was an advisor for the North America Business Consulting Group at Aspen from 2006 to 2015. He began his Aspen career in 1996, right? Wow, so long. Hold various analytical and senior roles. Before joining Aspen he was an APC engineer at Chevron Oil for 7 years. Mr. McCallum has a BS Chemical Engineering from University of Washington, Seattle, United States. Now he resides of Cleveland, Ohio, United States. Right. So please welcome Doug. Right. Say hi to Doug. Right.
Hey, nice to meet you all.
Nice to meet you. All right. So I will hand over to sorry, about housekeeping, a little bit of housekeeping. So you can comment if you have any comment, you can put it in the chat, right? If you have specific questions, you can put it in the Q&A. There's a tab Q&A on the right, right? I will make the handout available now, so you can also download the handout, the presentation deck. Just now I made it available. You should see it in the chat, right? Okay, so after this, the replay and the recording will be sent to the registered email, right? So yeah, so let's learn from Doug about APC. I will turn off my camera now.
All right. Thank you, Fauzi. And should I start? I'll start sharing my screen here. Okay. The title of my presentation or talk today is Getting the Most from Your Plant with APC. And target audience of this presentation is more of the process engineer, someone who doesn't have a lot of advanced process control experience. And this is just to kind of get people to understand the concepts of APC and some of the key things that to be looking forward and moving and going forward. So I'm going to kind of go over like terms and definitions and why you want to deploy advanced process control, and then kind of a little bit about what is advanced process control, how it kind of works. And then there's a key piece of advanced process control, which are called inferentials or virtual analyzers. And so I'll go into a little bit of depth about those, because almost every single advanced process control project has an inferential associated with it, and they go hand in hand. And then I'll go through a quick APC example, do some value, talk a little bit about how to estimate the value that you can generate with advanced process control. And then we can just open it up to question and answers, and keep this fairly informal. So what is APC? Well, let's set what the definitions are. APC stands for Advanced Process Control. It is a generic term for model predictive control, dynamic matrix control, multivariable control. So you'll see all these four almost used interchangeably. Like AspenTech's products called DNC, others it's called MPC. There's all sorts of different types of controllers out there. All in a sense, they are multivariable, model predictive, dynamic controllers. And so people just take a few of those words and put them out there. It sometimes gets confused with what I would call ARC, or Advanced Regulatory Control. And this is where you write code in the DCS, and it is constraint control. So if the temperature gets above this temperature, then increases flow by 1 unit of measurement or something. And some of these can be really advanced programs inside of a DCS, and they're very complex to program, and they take a lot of time and energy, where advanced process controls is 10 times better at solving the problem, and it's way easier to maintain. So why would you even want to do an advanced process control in the first place? Well, if you have quality issues, if the process has instability, if you want to, you're really trying to save energy and meet your CO2 limits, you may have production bottlenecks. You're running right at 100%, and you want to get it to 102, 103%, and you can. The APC can really get you that extra, 2 to 3% capacity. And when you look at the operational margin of that unit, that could be a tremendous amount of money. If you have operational inconsistency, if you notice between shift to shift, that on B shift, the plant runs great. On D shift, the plant horrible. A and C is okay. It's because they all have different operating philosophy. And if you want to have a consistent operating philosophy, 7/24, 365, you can put on advanced process control, and it'll get you that operational consistency. You could have interactive and competing control objectives. So on a distillation column, you have the overhead with the reflux and the bottom with the reboiler, and they interact with one another and trying to control the quality constraints. Having a APC on that will enable you to solve that problem and then really nail your qualities on the top and the bottom. You can have different constraints at different times. This is, during summer, you could be having problems with your overhead cooling. During winter, it could be adding heat into the reboiler where you have the different constraints. And so the constraint set will change with seasons, or it could even be as simple as like an LNG plant where it's the day-night cycle where you can get an extra couple percent throughput at night, and then you have to throttle it back during the day. And if you always are trying to operate close to that optimal constraints and keep yourself there safely, then APC is for you. So where does it fit in the typical technology pyramid? Well, at the bottom, the field level, you have the sensors, the valves, the instrumentations. This is in direct contact with the process. And then you have the control level. This is the DCS or PLCs. You got the PID loops. You got maybe some cascades. This is connecting to those sensors and those valves and manipulating and keeping the plant under control. APC is in that supervisory level. So it's writing set points to the PID loops. And it sits into the DCS architecture, the network. So it is down very close to the control system. And then on top of an advanced process control is a real-time optimization. It could be a dynamic, a steady state. It could be just a custom model, just something that where you can give external targets saying, I want maximum of XYZ product, and then I want to save energy, are the directions that the optimization wants. And then at the top, you have the planning level. This is the enterprise resource planning. It could be the LP that you have for PIMs for refining. Just something to help give you the overall targets that you then feed to the RTO, which then feeds to the advanced process control that goes down. So this is the typical technology pyramid. And when we get down to a little bit closer look at where the actual APC servers sit and how it actually interacts, is you can see the sensors and actuators here at the field level. And then the control level, you have the distributed control system or PLC. And there's typically a human machine interface for the operators so that they can interact and see the alarms, interact, change the set points, change process limits, always trying to keep the plant, in a typical safe operating space while making money. And then the APC server sits in that automation network, and it communicates via OPC, an open protocol, to the DCS system so that it's writing set points and keeping the plant in a very stable and most optimal position. So I've talked a little bit about model predictive control and dynamics. So you have a process, that's a square box, and you have a bunch of inputs, and I'll be calling them this presentation MVs, or manipulated variables. Then you would have things such as feed forwards. These are things that you can't change that are coming at you. That could be an example as the temperature of the outside weather. It could be the amount of feed that you have to process. It could be multiple different things, the product, the feed quality. And these can be unmeasured or measured disturbances. And they also are called DVs, or disturbance variables. And then the outputs are called CVs, or controlled variables. This is what you're interested in interacting and keeping the process in a very stable way. In a more simplified, you have the input. So you have this manipulated variable, and you make a step change, like a 1 unit up. We'll say it's feed rate. You increase feed rate by 1 unit, and the feed controller, PID loop gets it to you right there. And so it's kind of like a step change. And then you look at the column itself, and there's a certain amount of dead time where nothing happens. And then there's a response time where process starts to change. You're assuming you're not changing any other variables. You just increase that feed rate into the unit. And then eventually everything will stabilize and equilibrium out. And so you have kind of like a time to steady state. You have a dead time, you have a response time. And this is the brains of an APC. And you would have, for each one of the manipulated CV pairs, is you create a matrix of all these different individual models. And then they have plus gains, minus gains. They can have some very strange dynamics. And you take that all into account, and you run this on a minute-by-minute basis. And so the intent here is to be able to predict what has happened in the past. You use the data from the past, and then predict where the process is going into the future over a certain time frame, horizon. So it'll understand what all the moves that the controller has made, or if it was off, that what the operators have made in the previous hour. And it knows what the process through these models, what it's going to do in the future for the next hour. And it uses that prediction to be able then to optimize the path to the optimum. So make sure that you don't have any variable go outside and cause you to release a safety valve. And then it also pushes you to that optimum spot. It runs on a minute-to-minute basis. It can run as fast as 15 seconds. It really depends upon the process and how much horsepower, CPU horsepower you want to go. It runs 24/7. It is truly a multiple input, multiple output problem. So you do have, many hundred, not hundreds, dozens of manipulated variables and dozens of control variables, and you can put that into a matrix. And you usually size the problem to be able to take care of the whole scope of that process unit. So you're getting the most amount of value and are able to take into account the changing conditions and changing constraints through time. And APC is like having your best operator on his best day, running the plant 24/7. And operators, when they get these on, they tend to go, oh, it just lowered their blood pressure by 10 points. It makes their life easier. They get a lot less alarms. They're very happy. So you have to have like a model-based predictive controller. And from here, you would get the set points and parameters. It pulls the information of where all the control variables are, where all the disturbance information, the feed forwards, and it gathers all that information, and it models and it predicts what's going on. It does an optimization. It creates a move plan. So it's calculating. I don't have to move some MVs now, but I will in a half hour. I have to start increasing the reflux, but I don't want to do that now. But in 30 minutes I do, and then next time it runs, in 29 minutes I need to do it. 28 minutes, you get the idea. So the idea here is that it's always doing that, and it sets that information down to the plant, and then it remeasures and calculates, and it has a thing where it figures out how far off is it, is it erring? There's a prediction error. So it's understanding that it's always, and it's self-correcting as it's going through this path. And you get a matrix, and not every manipulated variable. The manipulated variables here are on this vertical, and the control variables here are on the upper limit here, or the top column. And you have a whole bunch of MV-CV pairs. And I kind of do this as an exercise. I'll talk a little bit more about this further in the presentation, but a bright green is a strong positive relationship. As bright red is a negative relationship. Light pink is a weak, and a light green is a weak positive. And so you go through and you'll have a matrix, and so some MVs will impact several CVs, vice versa. Some will, some CVs are impacted by a lot more. And this is the brains. And each one of these little models is like that squiggly that I showed you with that in the previous slide, where you have a step change, and then you'd have what the dead time and dynamic response and what the steady state gain is. And this all fits into this matrix. So it is truly multivariable. Then you have an embedded optimizer. So it's always looking at what is the primary thing you're trying to do, what's going to generate the most amount of money, and it's going to push you to those limits. And then it also hits all those, you include all the constraints. So if you have here, I have 9 manipulated variables, I should always have 9 constraints, whether they're a clamp on the manipulated variable or you're actually hitting a control variable limit, but it's going to push until you hit that limit. It could be as like the valve positions at 100%. You just can't get any more into it. They'll understand that, and it'll push all the things and move the plant a little bit more, so that it will always try to maximize the profit and get you that extra percent capacity. So how does it really work? Well, you have all these different constraints, and the operators typically like to operate the plant in, a very safe thing. They don't like alarms. They kind of push it a little bit towards what they think is the optimum, but for the most part, they just want to make sure they operate the plant safely and on spec, and everything's happy. So in this example, let's assume this limit is the amount of impurities in the product, and you'll have a variability of the impurities going up and down. And this is current operation, and it's all fine. Well, you want to reduce that variability and then be able to push the plant in a more closer to that limit. And whatever that delta is, it could be saving in selling that impurity as product, which will then make you a lot of money. It could be reducing energy, could be reducing the chemicals needed to be able to make that. So there's a lot of different things. It all depends upon your process that you're looking at. And then, so you go through like the calibration. So as you're doing the pre-test, plant test, and actually improving the model, the variability will slowly reduce, and you start pushing the bubble. You know, the bubble shrinks, and there's a little round circle, and you're getting closer to the most optimum point. And so the idea here is you're kind of on a trajectory. You're reducing the standard deviation, you're shrinking the bubble, you're pushing to the limit, and eventually you have a really small bubble, and you're in the corner, the most optimum, and the delta. And there always will be some variability due to, you know, unmeasured disturbances, things you can't predict, instrument error, etc. If everything is perfect, you should have a flat line and get it right there, but life is not perfect. So what are the typical benefits of advanced process control? I mean, quality standard deviation reduced by up to 50%. I've actually seen 80, 90% reduction. Yeah, energy consumption, you know, 10% easily. Product yield, if you're trying to increase, you know, that up to 3%, sometimes, you know, that could be extremely lucrative. Manufacturing capacity, or, you know, production increase, you know, depending on the process and how much focus has been onto it, 3 to 10%. And, you know, just by operating this in a very consistent and safe manner, you increase the reliability of the process as well. So I kind of talked a little bit about what an APC is. Now let's talk about that quality. You know, I was saying the impurities in that product. A lot of times you may not have an analyzer, or the analyzer runs and it runs only every 15 minutes. And if you're running minute to minute, you need to have some way to be able to bridge the gap so that you have a value to be running to, and it will see the impact of the process change so that you have decent control. So an inferential sensor, these there's a lot of different names. They could be called virtual analyzers, virtual signals, all sorts of different things. In a sense, they're just a mathematical relation that calculates and predicts a controlled property or a KPI or unavailable things. And it's using process data to be able to do it. And sometimes you use it because the measurement is extremely costly to measure that point, and or just impossible to put a measuring device. But you can use potentially a process simulator to create an inferential. There's all sorts of different inferentials that are out there, and they're very commonly used, and they've been used for, you know, throughout my whole career. Done tons of inferentials, and you use inferentials when you want to back up an existing analyzer. So as I was saying, that analyzer could be giving you an answer every 15 minutes. This way you can then have a process signal all the way along. And also it helps eliminate the dead time. So you know what happened. It may take it 15 minutes to run to give you the value from 15 minutes prior. You get some dead times, and you can get some strange analyzer cycles if you try to use those in an actual PID loop. And it also gives you a redundancy in case the analyzer goes bad, which is quite a common thing. And where if the analyzer starts to freeze and get stuck, you could sit there and say, okay, the analyzer is bad. And you always use lab updates and so forth. You know, I can't say enough about inferentials are a very key part of an advanced process controller. So when you're trying to build and develop an inferential, you'll get lab data, you get some process data, and you use model generation. So I tend to use like partial least squared. I try to incorporate, you know, process knowledge that, you know, these are the parameters that should impact it. You can go deep learning and neural net and other AIs. You know, they can help when there's some really significant nonlinearities. I also like if you can get a first principle model type inferential that takes into account those nonlinearities to be able to have it. And if you have to have something like a dynamic inferential, then some of these FIR models. Here's an example of Aspen IQ Online, but in a sense, what you need is an application that's attached to the DCS that is checking the model inputs. It's calculating an unbiased prediction, and then it creates that inferential, and it's good to coordinate with the actual APC, and then it sends an unbiased prediction down. And then once you get the lab data, you need to coordinate that lab sample time with the unbiased prediction. So, because operators, this is a very key point where operators will sometimes just slap, I take my sample at 8 a.m. every day. No, they don't. They take the sample when they get around to it, and you need to know kind of exactly when that lab sample was taken, so then you can get the process conditions at that time where that lab sample is, and then do a back check, and then what was the actual unbiased prediction at that time, and then you calculate a bias, which is just the offset. And this doesn't sound like a lot, but this whole online piece and coordinating and unbiased, there is a lot of time and a lot of bookkeeping, and can be quite daunting. And so it's good to use a commercial package in order to do that. So a good performing inferential requires data with good correlations between the input and calculated properties. They can be the same as when you're developing the APC models. And if you do have troubles making an inferential, you might have to do what we would call as an inferential campaign. It's a planned testing where you increase the sample frequencies, you make step changes to be able to get some really good inputs into the inferential. And having the appropriate input selection is great. Try to reduce the amount. There's nothing worse than taking 200 variables, throwing it into some black box, creating an inferential, and getting yourself a 0.999 R squared, and you put it on, it won't work. It just, you've overfit all this and erroneous data, and it will never work. You need to actually take the handles that actually should have impact on that process, on that inferential, and then you can use your process simulation knowledge to really be able to help in those selections. And you can try to choose and reduce and see what number of inputs to get you kind of like the highest R squared. It doesn't have to be perfect R squared for the error. And you always need to have that lab and analyzer feedback, because models will drift. And once again, I'll say it, and that's kind of why I have it highlighted blue. You really do need to incorporate your process knowledge. It's just not math and statistics. So, the inferential calculation techniques, I talked a little bit about this already, is, algebraic equation-based inferentials. It could be a pressure compensated temperature. It could be a PLS, a PCA type model. You can have deep learning, FIR, nonlinear. Anyway, you just need to have some sort of mathematical models. I personally like the PLS and the more algebraic type, because they're easier to understand, they're easier to explain to operators, and they're not black box, and they're very predictable. So then you have the unbiased. I talked a little bit about this, the unbiased steady state prediction. It's always good to keep track of that. And that's just the algebraic equation, and it's always calculating. And you are able then to trend it over time. And then you have a prediction error. And if you get the bias, and you can see if you're always getting a bias, and it may be related to a certain type of feed. So if you have two different types of crudes that you're always running, and the prediction bias is always 10 when it's running this crude, and it's 5 running this other crude, you can then just change that prediction bias automatically and not have to have it kept up. And so the bias updating is a very important thing, where this is, as the models drift and you'd have that prediction, do you take like half of that new value of the error, because the lab values could be just as bad as sometimes the actual values, and being able to have it and just be able to continuously update the model and keep track of it and make sure that and you need to let the software know that, there's a new sample available to be able to do all this updating and biasing and so forth. And so it's all very important. So, and there's usually, you can have a validation only where there's no bias prediction. That's useful in testing. You can have a traditional, which is like 50%, 80% of the value. You can set up 𝐘𝐸 score, a whole bunch of different advanced methods. And I like to do just the traditional method where you get like 50% of the value, and you can play around with what percentage of the bias update to be able to look at it. And so here's an example. I mean, this is a 0.6 R-squared. And, it doesn't look great, but it actually is a pretty good inferential. If you look over here, this is the time trend. And so it does do a pretty good job at tracking. And it takes, why it's kind of high or low in its R-squared is because there's a lot of variability in the lab measurement, but overall it's tracking with the average. And this was deployed and was quite successful. So now I'm going to kind of go into an APC example. So, this is just a simple distillation column where you have the feed coming in. It has disturbance variables of temperature and quality. You control the feed flow into this column. And wherever you see a yellow, those are the control variables. Wherever you see the green, that's a manipulated variable. And so here we're trying to control the temperature of the column by adjusting the steam. And I have broken the level controllers. That's why the levels are yellow. And I now have the output. So it's actually writing down to the valve output of both the byproduct and the product. And you have the different, qualities and the flows, and you're controlling the pressure directly there. And you got the temperature control and condenser and the reflux and the reboiler. So it's your typical distillation column. And so from here, you can think through the whole process. So you think about, what does the feed rate? If I increase it 1 unit, it's going to then increase the product rate. It's going to increase the product quality, byproduct rate, byproduct quality. It's going to have impact. Column DP, because you're shoving more material into the column. If you don't change any of the duties or anything like that, the temperatures are going to slump some. And then the pressure of the column, may go up as well. So you kind of, what's good about doing this exercise and going through and trying to think through the process is to come up with where you think the model should be on a physics, chemical engineering type basis, and where you would expect to see the models. And when you go through the testing phase, making sure that you get, before you start like an auto stepper, that you have at least 2 models per control variable, so that you can then have a very successful plant test. And so it's good to be able to look for where those potential models should be. And as you're going through the actual plant test and you're developing, you'd want to be able to see these models and these curves. And if you start to get some models that aren't showing up, you may want to ask yourself, why? Did we miss something? Is that something that should be added, shouldn't be added? And this is where you really want to utilize your process knowledge to help sketch where the model matrix should be. And if you have and it's really nice if you have a simulation model where you can then try to test the gains. You treat it like the control system set up at the actual plant, and you fix the overhead duty, the underhead duty, and you just increase the feed flow and seeing what happens and seeing where the gains and things that change. So now let's start talking a little bit more about kind of like value levers. And these are the main buckets that advanced process control can impact. And, some of these are, it may not, but it definitely, APC definitely is increased throughput in production. It definitely helps with the lower energy per unit of production. It helps with less raw materials per unit of production. It gives you a very consistent specification quality. And from that, by having a very consistent quality specification, you do get improved customer satisfaction. I worked on one thing where the project itself was, it was a payback, but it was like a 2-year payback. It wasn't a typical refining unit. This was a specialty process, and we were thinking it was going to be just a marginal project, but after we had run it and test for 3 months, the downstream customers, which was same company, were going crazy because it was saving them so much money by having a very consistent product that they saved the downstream impact was just off the hook. And so they were like, we need to have this everywhere. And so it was kind of an eye-opening, like just because immediate process here, the improving the product downstream can really help. By having these controllers on there, it enables the operators, the board operators, a bit more free time to be thinking about optimization, making sure safety. It just increases the overall productivity of the employees. And by not cycling things around and going from one operating mode to another, it does decrease a little bit of the maintenance costs and the reliability and so forth. And if you're always making on-spec products, you'll reduce your inventory reduction. And sometimes, if you're able to get that extra 2%, you don't have to do a major project or revamp it to add 5%, because the APC controller will get you that, so you can save some capital money avoidance. So what I do, most of these calculations are not, rocket science. And here that, I just did a 10,000 barrels a day, 350 operating days. You want to push this plant 95% of the time. It's $4 a barrel, 3% capacity increase. That's about 400,000. This is the type of typical. The only thing that really is questionable is the margin, which comes from you all, the customer, and then the throughput improvement. 3% is pretty much standard what you can get with the advanced process control. And this is how you can then quickly do a back of the envelope estimation what the value is. And here's, saving energy 3%. You should know how much energy your plant consumes, what your cost of energy is. This is obviously assuming there's a lot of cheap U.S. natural gas. And so it's, this would be like 5 times higher if it was in Europe. And then you have, if you have CO2 tariffs, what that potential value is. Yield, what's the difference between that byproduct and product, and if you can move some of that into it. Sometimes products, it's all about going to the moisture content of the process, so allowing the water to be sold as product. And if you're over drying, you're using more energy, and if you can increase that water up from 8% to 10% closer to its specification, you're selling 2% of your 2% water as product, and that could be a lot of money. And if there are some chemicals, and sometimes part of the process is you want to reduce chemicals added to the process in order to make product specification. If you can ride that lower limit, that could be where the money is saved. So going back to these different levers, looking at your process, maybe just a certain combination of these, but to be able to then to just quickly understand where the potential value is, do some of these rough costs, and you get a potential benefit. And that's 800. This one here, 850,000. That's 850,000 a year for the rest of the life of this asset. So, we'll go with question and answers. But I wanted to first off say, I hope I took away some of the mysteriousness of advanced process control, and that APC can be applied to almost any continuous process, and that there's significant value of advanced process control. So, I see.
Right. Okay, there are some questions. All right, the first one, what is the best reference material or certifications or course to start a career in APC?
I think, the AspenTech has a DMC3 certification process, and from there you can get DMC3 certified, which has a pretty good basic advanced process control knowledge. And you take their APC 105 course, and it goes through the whole process theory. Of course, it is very specific to AspenTech solution, but it is a really good course.
All right. Okay, next questions from Mohammed Siddiq. Which one better, APC, which using data collecting, or APC which use AI for creating data model?
So the question is, what is the best APC package out there?
Yeah, So you can click the question tab. Yes.
There we go.
Right.
Okay.
Scroll up. Yes.
What is your opinion on application?
The first one. Yeah.
Better? Yeah, which A? I like doing having a step test and using the data. You can get using AI and using historical data to create a model. You can get a rough approximation, but it's not going to really always save the problem. And you need to have a lot of data in order to make a good AI model. And a lot of our processes just don't generate that many years of data in order to create a significant AI model. And so using a step testing and a plant test and getting the data collection, you actually get some good responses, and you can look at it. And I saw on the other one where manual step testing, I like to do the automatic step testing, but you do need to be able to separate out some of the correlated variables so that you can determine and make sure that you're not creating yourself issues that when you put it on controller online, it'll go crazy. And the next question is, what is your opinion about application that involve use of fuzzy in the context of APC? From my understanding, what fuzzy controllers are more like the original constraint controllers, or rule-based, where there's if you're between this value and this value, you should set this value to this value. And they're okay, but it's more of, you're not going to get, you may get like 20% of the value, and they're very difficult to maintain, is my opinion.
Okay.
What industries are already using APC in the world? Because I also use APC in the pulp and paper industry. The APC started, that I know of, in the refining and petrochem space. So the big ethylene plants and the refiners, and then almost all the bulk chemical processes. Those are industries that AspenTech really focused on. I do know that APC is in the pulp and paper industry in some regards. APC is also metals and mining. It's also being adopted into food and beverage manufacturing, and then also even in some consumer product goods as well. And so I've seen it installed on some very unique processes that you wouldn't even think of.
Nice. Okay.
If I want to apply APC on a crude distillation, but some of the critical parameters affecting the specification of products are not being on flow meter for the last few years, like it's being injected into the column based on guessing the flow control valve opening percent panel up. So how can you deal with this problem? And I want to apply APC. That is a very, very good question. And that is where a typical project has what we call a pre-test, and that's going through the process of looking at where all the instrumentation, checking the valve, checking the tuning to make sure that the PID loops are in good working order, and do they have enough pieces of information. If you can't create an inferential for some of these key variables, you won't. If they're adding something to the column without a flow transmitter and it's guessing, and so it's random, that's going to be a problem. And you need to create what the potential value of putting advanced process control is on that, and then estimating the capital cost of adding the flow meters, adding that needed instrumentation, and putting that together with the APC package. So it's no longer just an APC program. It's a crude distillation modernization program where you add in that instrumentation as part of the project. And you'll probably have to wait till the next time you do a turnaround, or if you have everything ready and you have a short mini turnaround, being able to take into account. And it's good to be able to take a look at and see what's critical, what's not critical, And usually when I do a pre-test is I'll list like, these are the critical pieces of information. You need to have it, or otherwise, we'll wait until you get this information. Others are moderate. I mean, we can do it, but we really want these. And then others are just really like nice to have. It'll help, and it could be for informational purposes.
All right.
How does APC contribute to predictive maintenance strategies, and what are the key indicators it monitors? The main thing that APC will contribute to predictive maintenance strategies is it just stabilizes the process. And if the predictive maintenance can tell it that, hey, you need to have that level of that knockout drum always below 50%. And if it gets above 55%, then we start having some liquid carryover, which causes issues. Making sure that that controller always honors those new process. That's how they can work together.
All right. Okay, I think next questions. I think this is maybe a bit misunderstanding. Which are the advantage of McCallum APC compared to APC from data parsing?
What are the advantages of McCallum's APC compared to APC from Data Park? I don't know what Data Park is, and I'm just a consulting company. I don't have an actual APC software.
Yeah.
I prefer AspenTech's APC software, but I am APC technology agnostic.
Yeah. All right. Mohammed.
How long data modeling is robust, and when we have to conduct remodeling data, as long as not to revamp capacity. If I can understand this, usually build a controller, and if the plant will slowly change, and you may want to go through and then do a quick test or model update. It's good if you're able to put the controller into like a mini test and gather some new data and then update the models. AspenTech's DMC3 has a really nice capability to help support that work process so that you're always keeping the controller pretty close to peak performance throughout its life. Others, you may have to just monitor it. You can maybe change the gains a little bit, see where things are going, and kind of keep the controller in decent shape. If it is a major change where if all of a sudden you're changing out from trade to pack columns and doing some major rework, well, you probably all have to do some sort of a revamp. You usually will have a lot of the interface down. The operators will know the game. So the revamp is not a complete rework of the whole project, but it is a little bit more of a significant project.
Okay.
To start, I actually think a good process engineer is a good base layer before becoming a process engineer. Because I did start my career as a process design engineer. I was designing hydrocrackers, and then I went to a refinery and was a process engineer before actually becoming a process control engineer. And I think having that kind of a skill set works. I mean, I've seen good people come into the APC when they didn't have a good understanding of the DCS layers, but it's more of being able to think of the process, and if I move the feed rate, how is that going to impact everything, so that you can then have a really good understanding.
All right.
And how you get benefit from Aspen HYSYS dynamic model and APC can use it. Actually, that's a very good question. If you have an Aspen a HYSYS dynamic model, we have done testing on the HYSYS dynamic model to get a pretty decent model off of it. Especially depends on how well that dynamic model tunes to the actual plant itself. And then you can put that controller on the actual process itself and then do some slight calibrating just to make sure that it matches up. And then you can use some of that information back in to help improve your dynamic model. That's a very common thing that was done for offshore platforms, because they usually always have a dynamic model on their process, and just to step test the dynamic model to create the first pass controller. FIR models are and FIR models and subspace models differentiate? Which ones are better? That's a kind of a religious question. And I kind of like the subspace models, just like, but I'll take a look at them. When I do my identifications, I do both FIR and subspace, and I take a look at them, and I like them when they all agree. And if they all don't agree, then I start to try to ask myself why.
All right.
Let's see. It's like subspace, find the solution between pens. It's using FIR and subspace identification to be able to figure out what's been happening in the past. And it's also, when the controller is running, it knows it's made moves of this manipulated variable throughout its history, and then you can then sum where it should be going into the future. And so it's part of the mathematics of the actual controller.
Okay.
Ask
the question.
Which are the controller parameters in APC controller, and how do we perform tuning to determine optimal parameters? That really depends on the APC product itself. Each one has different names for their tuning parameters. For DMC3, that would be equal concern errors is one of the things, and then you have LP cost. It also, but what's really nice about DMC3, it has a module called Smart Tune, which you sit there and say, I want to make this product, and then the next thing I want to do is I want to reduce cost, and you can then have a multi-layered optimization, and boom, it'll help you there. And for the actual tuning, there's a simulation capability, so you have move suppression. So it's like, how fast do you want to let the manipulated variable move, and boom, boom, boom. And so you can change those tuning parameters and you can then test it with that simulation to see how well it works, how well it does in rejecting disturbances. Does it go nuts if you have a big change? And so you can change those parameters. And that is where some of the black art comes into from an APC engineer. Okay. Regarding the question about remodeling, is there an option to apply recursive subspace identification to capture strong nonlinearities? Possibly. That's beyond my skill set on that one. I think that's a good question for some of the research people. I'm more of a practitioner and using the tools out there and solving problems and getting results. Layered base optimization like APC, RTO, and multi-unit optimizers, or full scope AI optimizers with resource reinforcement technology. Thoughts? I like the APC as a base layer. A good advanced process control that's monitoring all the constraints. It's running. It's been proven, and it solves the problem, and it's really good. Then whether the question to go to an RTO versus a multi-unit optimizer or an AI optimizer, it depends on what you're really trying to solve. If it's a chemical plant that you can you have completely modeled in a process simulator, and you can then do a real-time optimization that can solve, and it solves within once an hour, and can write the set point down the APC, that's probably good enough. If it's something where you have a whole chain, a whole bunch of linked controllers or linked processes, and you're trying to optimize the overall plant, then a multi-unit optimizer. I haven't fully seen an AI optimizer completely be successful yet, so that's still a new technology. I know that's the hot topic out there, but it's we'll see. My opinion, jury's out on that one. And there are some capabilities where there are some AI units which take the model, like the RTO model or the first principle model, and they do a physics-based type regression of that model, and you create a hybrid model, which then can run extremely fast. And that can also help you with your optimization algorithm, or you use that, you plug that into something like the RTO, which then takes care of the heat and energy balances, because most AI optimizers don't have an understanding of heat and energy balances, heat, mass, and that's a very key oversight, and that causes those technologies some serious issues.
All right. I would like to give Doug opportunity also to share about his company, right? So we can maybe share that.
Yeah, like an introduction about who is McCallum Value Partners, or I like to nickname it McVeep. We're an APC consulting company that develops and executes APC programs for companies, and doesn't matter what industry. And we provide detailed benefit analysis. We can do that as well with economic scope and justification of projects. So we can help you develop your project list, help you develop justifications. As that one example about what instrumentations are needed, I can tell you what instrumentations will be needed, and then you can get your own E&C people to justify the cost projects, but we can put together a program plan so that this way you can take it and get capital funding. And then we also conduct APC benchmarking and gap analysis studies. So we can come to your site, and if you're a refinery and only halfway implemented, we can sit there and say, this is potential value of going to a full implementation. And this is where you kind of stack up against others. So we're a fairly new company, but we're growing fast.
All right. How can people reach you?
The best way to reach me is, I don't have it in there. Let's see, DM me via LinkedIn.
All right. Okay. I can include that in.
I
all right.
Use the outdated thank you slide.
Yeah. All right. I think there are two pending questions. We can answer that later on, or we can up to you. Right, from Akash and Akbar. We have 3 more minutes.
Yeah, let's go ahead and answer them so we can be done there. Do you have any experience using semi-empirical based models based on mass and energy, input-output relations based on equipment characteristic curves, base model utility systems where dynamics are too fast in seconds? Yeah, I've done a little bit on that. That is a very tricky things, and being able to, utility systems where things have to, you want to run those controllers at the 1 second level, and sometimes you have to put overrides down into the PLC DCS systems to keep you from overpressuring a system where all of a sudden you lose a part of the plant, and then the pressure will go sky high, being able to take into account. And APC needs to integrate seamlessly with existing process control. In some cases, legacy equipment may not be compatible or require upgrades, further increasing costs, take a long time relays, which may not be acceptable for some businesses looking for quick results. How to identify which units or systems are suitable to use APC and provide best options. That's kind of one of the things we do is we'll go through and we look at, what is the control system? What would you potentially need to be able to implement? As long as you have a decent OPC server, that tends to be all what you need. And actually buying the servers sometimes can be a bottleneck, and help you put together the business case so that you can go forward. I just want to say one thing is thank you, Fauzi, the Curious Engineer, for inviting me on today. I've really enjoyed it, and I hope you all have gotten something out of this presentation.
All right. Thank you so much, Doug. Right. I saw one comment from Amin, extremely accurate presentations with all the brief knowledge that could be discussed in a short time. Wow. Right. Thanks a lot, Doug, for the sharing facts with the knowledge, right? And maybe we'll see you again sometime on a different topics, right? All right.
Absolutely.
Thank you, everybody, for joining. All right. Have a good day ahead. Good evening. Right. All right. Bye-bye.